Okay, question 10. Which code fragment will produce a multi-qubit gate other than a Tafali? So again, to get to these questions, go to the video where we go over questions 1 and 2, and we go over how to access this document in the video. Which code fragment will produce a multi-qubit gate other than a Tafali? Like question 9 that we went over in the last video, I'm going to switch screens here, and what I Googled was Qiskit quantum circuit API, and I'll do it live just so we can have an understanding. Qiskit quantum circuit's all one word, circuit API. Should be this first one. If it's not, click around to see if you get to the right one. And this is a library of what we're capable of doing. So this will be useful for this question. Okay, so starting from the bottom, option D, qc.cry, and then these are the arguments. So when we look at it, we notice that it's ry, which means R stands for rotation, which means it's a rotation in the y-axis on the block sphere. So for this question, it's asking us to set up a certain gate. It's called a Tafali gate. A Tafali gate is a 2-input CNOT gate. So you can call it a CNOT gate with 2 inputs, or Tafali. Tafali is just a special name it's given. So a rotation on the y-axis of the block sphere is not what we want. So I'm guessing the rationale for it says something similar. Let's see here. D, controlled y-gate rotation is not equal to Tafali. So yeah, that's what we just said. So let's go up one. From Qiskit, so the importation blocks are normally pretty safe. So from Qiskit.circuit.library, import cxgate. So we're importing the function so that we can use it, or the library so that we can use the function. So that's pretty safe stuff. Normally, they don't try to trick you up with any of that stuff. So that's safe. CCX, so we're establishing this to be a CNOT gate, so CX, CNOT, same thing, with a control. And if we're talking, in theory, a CNOT gate, a Tafali is a CNOT gate with an additional control. So here in option C, what they're actually doing is going the long way around getting the desired result, but they're going the long way. So what they're doing is they're making a CNOT gate with an extra control, which is what a Tafali gate is. It's a CNOT gate with 2 controls. So what they're doing is importing it, creating a single CNOT gate, and they're adding another control onto it. So they end up adding this CNOT gate with these extra controls on it. So C is a long way of going about it, but it is correct. I want you, again, remember, there are a lot of paths to get to the correct answer, and this is one of them. So C, let's see here. They took a longer route, but this is still correct. So yeah, that's what we went through. Okay, B. So C is a bit of a design philosophy. We can throw another control onto this CNOT gate. B is less of a design philosophy and more of just a straight up alternative option we have. So MCT, we saw it again in 9. The M in MCT stands for a multi-control. So in our case, we want 2 controls. So we'll see 2 input controls for the multi-control. So here we see the 2 inputs, 0 and a 1, and then the target, the 2 right here. So right here it says MCT, and then we actually have the format, so this is pretty useful to know. So I guess I'll just, here we see the syntax for the MCT. It's control 1, control 2, and then the target. So here we see for this MCT, right here, 0 and 1 are the control qubits, and 2 is the target qubit. So I'll go ahead and switch back to the quantum circuit API library, and then we'll see, we'll search, control F, MCT. What comes up? Apply MCX gate, so we click it to get more information. Let me zoom in. All right, it's here. So here we have the syntax, so the control qubits and the target qubit. And then these things are, additional information. And ancilla bits are like, we use it to get a certain piece of information, we can throw it away. So ancilla is ancillary, it's just something we use to get useful information, but that's not needed here. So MCT is the multi-control gate. And then what makes it important in the situation, compared to question 9, we used MCT, but that one only had one control, which is a regular CNOT gate. Regular CNOT has one control and one target. A Tafali gate has two controls and one target, which is what we're working with here. So that is why MCT is a valid option. And then QC.CCX. This is probably the most straightforward way of implementing it. It's a control CNOT gate. So the C before the CX is a control. It stands for control. So here we have the same syntax as the MCT. So control 1, control 2, and the target. But please notice Qiskit in the developer certification exam is very finicky as far as syntax goes. So please notice that MCT has brackets for their two controls, while CCX does not have brackets. So try to remember that. So in question 10, we have two different ways to implement the Tafali gate directly. So again, Tafali gates are CNOT gates with two controls and one target. So we have .ccx, we have .mct. The third option that was correct is doing a regular control, a regular CNOT gate, and then adding the control function on top of it. So it's going the long way around, but it does get us the result we want, which is option C. So a regular CNOT gate with a control appended onto it, or with a control on it. And then we toss it all together with the append command. And then D was incorrect because the R in this CRY is a control rotation in the Y-axis in a block sphere. So that's not related, well, that's not a Tafali gate, so that's not what we want.